what I'll be presenting today is an opportunity to use these free surface multiples in imaging. And we also use the internal multiples and primaries as well. Now, this morning I was just thinking out loud, and autofocusing imaging is probably not the right title for my talk, because you have seen Rule talked about not just autofocusing imaging, but also redatuming and doing all these additional stuff in addition to imaging with autofocusing. And this is what I'll be presenting today. So I'll just give some background on the autofocusing, similar to what Rule talked about. It's when I define a Green's function, I define the Green's function as the response of a virtual source recorded at the surface. And this Green's function is convolved with a wavelet. Now, an important part in my talk is the coconut tree. Every time you see this coconut tree, that means we have free surface multiples present in our Green's function. And as well, to include these free surface multiples in the Green's function, we require the same things as the Green's function that Rule just presented on. A smooth velocity model as well as the reflection response. Now this is exactly the same thing that is needed for, let's say, conventional imaging like RTM. You need this smooth velocity model and also the reflection response. Now, in our Green's function, we can decompose this Green's function, and you can see the map in the CWP report, into a downgoing Green's function. And in this case, I have this superscript plus in the G, and that means it's downgoing at the virtual source position. And we can also have the upgoing Green's function, G minus. And the addition of these two Green's functions gives us the total Green's function. As you has talked earlier, you can use these two Green's functions, up and downgoing Green's function, to do imaging. Now, for this virtual source, as you start moving it, I'll just give some intuition on how the imaging works, right? As we move this virtual source, which is the green dot, closer to the interface, you can see that the downgoing leg of G plus at the virtual source, that blue ray part, becomes smaller and smaller. And at the actual interface, the downgoing ray part disappears. So intuitively, what does this mean? Like if I were to just cross-correlate G plus and G minus, events of similar time will appear at zero lag, and this is actually an imaging condition. This will contribute to our image. So in my CWP report, you'll see that for autofocusing imaging, we use this deconvolution imaging condition. And this really stems from Claerbout's paper, where he says at any arbitrary depth level, once we can define the up and down going wave fields, we should be able to get the reflectivity below that arbitrary depth level. And so I would like you all to remember just this symbolic equation here. And when you see this superscript 0, that means there are no free surface multiples present. Although the Green's function that are G plus and G minus do have free surface multiples. And you'll see the application of this later on in the presentation. So this is where the convolution imaging condition stems from. Now, before I go into some numerical examples, let me first acknowledge one of Rule's past students, Filippo Borgini, and his work with Case Wapana and these guys from Delphi. And what they did is they retrieved the Green's function that included the primaries and internal multiples. So first, what we do is we take R, and you see there's no subscript 0. So there are free surface multiples. We do SRME, surface related multiple elimination. We get R0, and then we apply Filippo's autofocusing algorithm. So we go from R0 to G0, and this G0 includes primaries and internal multiples. Now, this is just a 1D equation here, but we can go exactly from G0 to G. But this is a tortuous path to go from R to R0 to G0, then to get G. What we can do, and we can go directly from R to G. And this obviates the need for SRME. We actually naturally include the free surface multiples in the Green's function. Now, I'm not big on the equations. You can see the details of the equations in my paper, but in simple terms, symbolic math, my Green's function, the previous Green's functions, G0 was retrieved with R0. So we required SRME in this case. However, the Green's function that we retrieve, we use the full R. So the free surface multiples are also included in this R. And also, all we do is we just add this integral, which accounts for the reflections downwards from the free surface. While I was on acknowledgements as well, I also like to acknowledge my CWP colleagues, and especially Esteban Diaz. He has helped me a lot in understanding the imaging in conventional, and even some help in understanding imaging with these Green's functions. So let's move on to some numerical examples. And this is a very simple two interface numerical example, but it's a pathological example. And you'll see what I mean by that. So the model was constructed such that the primaries and internal multiples are 0.5 intervals away from each other in time. So we have a primary at 0.5 seconds, second primary at 1 second, and then the associated internal multiples coming in. Of course, we can have free surface multiples as well. And again, the free surface multiple, it starts at 1 second, but it's at 0.5 intervals, these free surface multiples. And this is the reflection response in 1D, what we'll get. And you can see what happens here. Because the free surface multiples are so strong, it cancels with our second primary. And this idea was taken from Weglein's and Dragoset's geophysics reprint series in multiple attenuation. And what we see here is that the second primary cancels with the first free surface multiple. And at later times, at 0.5 intervals, there's destructive interference between the free surface multiples and internal multiples. Now, if we were to try and do RTM, let's say on this model, we first need to remove all the free surface multiples and then apply RTM. But if in SRME, if we were to try adaptive subtraction, we predict the multiples and we adaptively subtract from the multiples from the data, we have issues removing this primary, because it cancels with the primary. The free surface multiple cancels with the primary. So we have some issues in retrieving it. However, in autofocusing, what do? We get the Green's function for the model itself. So in our Green's function, we will have this reflections from this interface. We will have the reflections from the interface because we do account for these free surface multiples. Let me show you. In the downgoing Green's function, G+, for a virtual source located somewhere in between the two interfaces, in this case it's 1,000 meters, it's exactly in between the two interfaces. One interface is at 500 meters, the other one is at 1,500. And this virtual source, you can see there's a downgoing, you just see the downgoing reflections from this virtual source. And there's one at 0.6 seconds that is reflecting from that interface, which was initially missing in the reflection response. Also, there's one at 1.1 second, and this includes the free surface multiple as well. And you can see these events in the downgoing Green's function. Now, the total Green's function at this virtual source is shown in yellow here. In black is the actual modeled Green's function at 1,000 meters in that model with the exact velocity. And you can see we do a pretty good job of retrieving the Green's function. All we required is a smooth velocity model and the reflection response. That is it. Now we can do autofocusing imaging, and in yellow is the autofocusing imaging result, and in black is the true reflectivity of the model. And you can see our autofocusing result gives us a pretty good match with the exact reflectivity of the model. Now if we were to move on to a more complicated model, yes, it's still 1D, but we have a very high impedance layer, generic of what we see like in a salt regime. And the red dot shows you the virtuals for just this virtual source, the retrieved Green's function. Again, in yellow is the retrieved Green's function, and in black is the model Green's function with the exact velocity model. Again, to retrieve this Green's function, all we need is a smooth velocity model and the reflection response. And now, remember, we can retrieve G0 if they by numerical means by just having an absorbing boundary at the top. And G0 only includes what? The primaries and internal multiples. The G that we retrieve here includes primaries, internal multiples, as well as free surface multiples. So the difference between G and G0 just gives us the impact of the events caused by just the free surface, which is in yellow. In black is G0. So initially we were imaging with G0, but in yellow these are all the events that we were missing, and they are so strong because these are the events that reflect from the free surface, and this strengthens the point that we should be imaging with the full G, all these events, instead of just the black events, which are G0. Now again, here's in yellow, the autofocusing imaging result, and in black is the exact reflectivity of that model. You can see we also get a pretty decent result with the autofocusing imaging. It matches up quite nicely with the exact reflectivity, which is shown in black in the background. Now, autofocusing is not just about imaging. We can do redatuming as well. We can also do this thing, I call it autofocusing SRME. So, remember that equation I told you all to remember? R0 is equal to the deconvolution of G plus and G minus. In this case, right just below the free surface, if we can get the up and down going Green's function, we can get this reflection response as if there were no free surface, which is shown in this case. I changed the convention, it's in black. In black is using the reflection response with free surface multiples and a smooth velocity model. We get the data as if there were no free surface multiples, which is shown in black. In yellow is the actual modeled reflection response without a free surface, and you can see here it matches quite nicely. There's some slight bringing, but in the grand scheme of things, it's a pretty good match, right? Now we can use this reflection response without free surface multiples. Unfortunately, you can see the X on the coconut tree, sadly, and we can do RTM, and this is the RTM result in green, and in black is the true reflectivity. And yes, RTM gives us a pretty decent result as well, but note we had to remove the free surface multiples from the reflection response. Also, if you were to look at the red circle, you see there are some slight blips on the RTM result, and this is due to the internal multiples from within that high impedance layer. Now, in terms of imaging, this might be very insignificant, but I just want to draw your attention to it because in autofocusing, we take into account these internal multiples as well as free surface multiples. And this is again the autofocusing result. You see that those blips or glitches does not come into play in the autofocusing because we do take into account these, again, free surface multiples and internal multiples. Now, what we can also do is we can redatum our data because the soil creates these internal multiples, yet small, but in this case it could have large internal multiples, so we can actually redatum. We can go below the salt And we can play like if they were receivers, sources and receivers below the salt. So we'll avoid the impact of these internal multiples within the salt, or whatever overburden we have. If we have a complex overburden, we can avoid that the complex wave parts and above, and we can make a new acquisition, let's say, I would say a virtual acquisition, as if they were sources and receivers at that new datum level. And here's the result. So we get R0 again. R0, there's no reflection, there are no free surface multiples. In black is the retrieved R0 below the source, so we don't get the effect of the internal multiple. And in here was the exact modeled reflection response without a free surface. You see, we get a pretty decent match. Yes, again, it's ringy, but that's because of the convolution to get R0. And now you can apply any imaging algorithm that is fashionable to you with this new reflection response below the salt. Let me summarize, before I end, let me just summarize what autofocusing can do. And again, I know you have heard me say this many times, but this Green's function that we show here retrieves what? The primaries, the internal multiples, as well as the free surface multiples. And all we need is the reflection response, as well as a smooth velocity model, which is what is needed for conventional imaging like RTM as well. And once we have this Green's function, we can do imaging, which includes primaries, internal multiples, and free surface multiples, but we can also do ASRME, which is autofocusing SRME. We can actually remove the free surface multiples just below the free surface. As well as we have a complicated overburden, we can get R0 below that complicated overburden, so we won't get the complicated wave parts of whatever is above it. I made a mistake in the beginning. I did not mention my co-authors. They were such a big help to me. Kees Wapana, Jos, Vandenhout, Everett Slav. Jyoti has been a big help as well. And of course my advisor, Ro. So I'll leave you with this picture of back home, and also with the sentence that autofocusing imaging is a natural way of using these free surface multiples, primaries, and internal multiples. And now I'd like to entertain any questions that you have.